there, ATS 211 students. Dr. John Schrage here, and I'm back. I have a video camera now, a new camera, and it's working. And you guys are back to the top of the queue for getting videos made. Again, I was behind in several courses, but we're okay now, and we are ready to get going on our 9th day of the class. And as we get going today, what we're going to be doing is we're going to be learning about another important weather analysis technique that we're going to be using as we learn more about forecasting and so on. And this is this whole story about positive vorticity advection. Now, you might think, hey, I think I remember that even in like the ATS 113 textbook or in my lectures or whatever. And that would be great if you do remember that, because that is the same thing. That's still what we're talking about, is this idea of how positive vorticity advection is related to what goes on in large-scale meteorology. Now again, this is not a WXP plot that I'm showing you here. This is a DIFAX chart. This is a standard chart produced by the National Meteorological Center at the World Weather Building and sent out over the internet. It used to be sent out over faxes and so on. You can tell Dr. Schrage is really old. And the dashed, this is a 500 millibar chart, so it's an isobaric chart. And so we're only seeing features that are in the atmosphere at the height above the ground where it's 500 millibars. And the solid contours on this rather messy plot are the heights. And so we could assume, because it's pretty high above the ground, that this is geostrophic conditions and the winds are parallel to these height contours and so on. All the good stuff that we like to be able to do. The units of those solid contours happen to be decameters or tens of meters. But it's not relevant for what we're doing. And the dashed contours on here are absolute vorticity. I'm not entirely sure what that means. Well, I am sure, but I mean, from a teaching point of view, that's where we're going to be heading with this. But, you know, we got two types of contours on this plot, and one type of the contours is the kind of thing that the winds follow or are parallel to. And therefore, if we look for solenoids on this plot, we could find areas of advection. In this case, it's positive vorticity advection, because we are transporting areas of greater vorticity. And, you know, I highlighted a couple, 3 areas right there. And that is a diligent atmospheric science student kind of thing to do. I mean, I could give you a map, or we could make maps on WXP that had absolute vorticity. We don't know yet exactly what absolute vorticity is, but I could make a map of it. And we could put another set of contours on top of it that were like height, so we know what the winds were doing. And we could make and find areas of positive vorticity advection. Positive vorticity advection, or PVA. But that would require actually trying to figure out a lot of stuff. I mean, in many ways, this is important. Many, many years ago, as a student in an atmospheric science department, I learned about positive vorticity advection. And on maps just like the one I was just showing you, I dutifully colored in with my red pencil the areas that were positive vorticity advection. And it's very possible that the person who taught me that very carefully explained why it was important and so on, but I have no memory of that. It's very possible that I was just a crappy student and I was busy, I don't know, thinking about something else when I should have been listening to the teacher. But it wasn't until years later that I understood why this all mattered. What was absolute vorticity? And why did we care about its advection? And why do we care about any of this stuff so much? It took me a long time before I understood that. I'd like to save you those steps and those mistakes, the way I made. So let's kind of walk our way through this again. First off, vorticity. Now, even in the ATS 113 textbook, there's actually a lot of information about what we mean when we say vorticity, but it's kind of, it's not the whole story. I mean, in classes like 113, you're going to have learned vorticity is the spin of the wind. It's a measure of how much the wind is spinning. And that's not hard to picture when you're talking about something that obviously is spinning, like a tornado, or something that is obviously spinning, like a mid-latitude cyclone. I could picture that there probably is some way to measure how and quantify how much that is spinning, or like that hurricane. Okay? Things that are overtly, obviously spinning, I can picture that there's probably a way to describe, based on observations from the winds and so on, how much it is spinning. But what's educational here is to notice what these 3 storm systems that I just presented to you have in common. And that is, namely, that their rotation is horizontal around a vertical axis. Okay? So like the winds are rotating this way, and there's a vertical axis around which they are rotating. Whether we're talking about the tornado, or the mid-latitude cyclone, or the hurricane, they're all examples where that is the kind of rotation. And from a meteorological point of view, that's the kind of rotation, the kind of spin we care about. I mean, it's perfectly interesting and useful to talk about how air's spinning this way, kind of like the direction of like a Ferris wheel or something, or a wheel on a car. That's actually, with a horizontal axis. In fact, that is an important topic in meteorology. That's called helicity, but we're not to helicity yet. When the axis is vertical and the rotation is horizontal, that's called vorticity. Well, even more specifically, that's called relative vorticity. What you learned about in Intro to Meteorology or whatever as vorticity is more correctly described as relative vorticity. And the symbol for relative vorticity is a lowercase Greek letter zeta. Now, I don't particularly care for the zeta that happened to be rendered in this font on PowerPoint here. You may even need to go as barbaric as go into like a Google image search on the letter zeta and see a better example of what a zeta looks like, because I don't happen to care for this very much. But relative vorticity, the symbol for it is zeta. And in fact, it can be computed. It is not something we measure. There's no relative vorticity meter. It is something that we compute based on the winds. And there are, actually it turns out 4 different ways to compute the relative vorticity. I put 3 of them here. I didn't put the 4th one in because it was cluttered enough. I don't expect you to memorize these equations or anything like that. I just wanted to illustrate that it is something we can compute. And in fact, we have a number of different techniques to describe this idea of spin. But it is something you compute, and you don't just compute it for the cyclone or for the tornado. In fact, every location on the map has a value of relative vorticity at every given time. And for that matter, every height above the ground has a relative vorticity. Just like you could measure the temperature at every location, or you could measure the winds at every location, you could compute the relative vorticity at every location. Now, it's a number. We could contour it. We could make a contour map of relative vorticity. In fact, there is one. This happens to be, again, made by WXP and that old software, that old data cases there. And there's a map. And it has, I should have put a bar on it, but it has areas where there is positive vorticity and there's areas where there's negative vorticity. Positive vorticity is defined when the wind is spinning in a counterclockwise way, and negative vorticity is defined when it is spinning in a clockwise way. And just to show you how this is related to what the winds are doing, I've taken that same map and I have overlaid upon it the contours of the height at 500 millibars, which, is kind of like isobars. The wind blows parallel to them at those heights, because we're, like 5-6 kilometers above the ground at this point. What do I see? Well, for example, see that area of positive vorticity, that bright red area over Nevada? See how that's associated with how the winds are curving in a cyclonic manner. They're turning counterclockwise over in a trough over Nevada and Utah. But I can see that some of them it's much more subtle. I mean, like for example, see how we can see in the vorticity over Indiana and Ohio and northern Kentucky and so on. There's that area of positive vorticity, and you can kind of see in the winds there is a little bit of a trough, just a very subtle one there though. Okay. These are related. Positive areas of vorticity, of relative vorticity, mean that the wind is turning in a counterclockwise way or cyclonic, and areas of negative vorticity are turning in a clockwise way or anticyclonic. Here WXP just made those calculations for us and actually took the winds and actually computed the vorticity at each of the relative vorticity of these locations. Hey, take a look at the units there. If you actually look at the top of the graph there, it says 500 millibar relative vorticity in units of 10 to the negative 5th per second. The important thing here is per second. The units of relative vorticity are per second. Think of that as like rotations per second. Okay? So, like if something were turning at a certain rate, it's how many per second it's doing. So it had to be turning pretty fast to even be one rotation per second. I mean, anything, even a tornado doesn't go all the way around the outside of it. The winds don't go all the way around there in 1 second, okay? It's going to be a small number. In fact, it's a very small number. It's 10 to the negative 5th per second. Now, it's not exactly rotations per second. That's not quite the right interpretation. It's actually radians per second and so on. But that's a good way to kind of visualize what it is. It's a measure. It's actually, from your physics classes, you might remember from when you did rotational motion. It's an angular velocity. So it's in it's in radians per second, but whatever. Okay. And they're small. For something like a trough, it's on the order of like 10 to the negative fifth per second. Meaning it would take a single air parcel more than like a day to make a full rotation, going, a full circle. But wait a minute, those maps that I've been showing you so far, they're relative vorticity. There's actually a built-in variable in WXP called rvort for relative vorticity, and that's in fact what I've been showing you. But that isn't what was on this horrible looking plot that I showed you here. This is absolute vorticity. Absolute vorticity. What is absolute vorticity? Well, I can tell you mathematically easily enough. Absolute vorticity is the sum of relative vorticity and planetary vorticity. That helped, right? No, that doesn't help. Absolute vorticity is the sum of relative vorticity and planetary vorticity. The symbol for absolute vorticity is a little lowercase eta, which looks weirdly like an N. And it is the sum of relative vorticity and planetary vorticity. Relative vorticity is that zeta, so planetary vorticity apparently is F. So, wait a minute. Okay, what is planetary vorticity and why is it F? Alright, well, planetary vorticity. Planetary vorticity is the component of the absolute vorticity that is due to the fact that we are on a rotating planet. Even as I sit here in my chair, in my office, I am rotating. I am rotating about the axis of the Earth at a rate that's pretty easy to understand. Once every 24 hours, I get all the way around 2 pi radians. I could figure it out. But that's a little bit misleading. See, not all of my rotation here is horizontal with respect to a vertical axis. I mean, hey, I'm sitting in a spinning chair. I'm going to show you relative vorticity. Whoops, I think I will if I don't hit the table. Look, relative vorticity. I'm spinning with respect to a vertical axis. But I'm also spinning with respect to the axis of the Earth, right? I mean the axis of the Earth as I'm going around, but the axis of the Earth is complicated. What direction is the axis of the Earth? That's north, but the axis of the Earth isn't like parallel to the ground, and I'm at 39 degrees north. It isn't exactly parallel to the ground, it isn't quite straight up. My rotation around the axis of the Earth is not exactly a horizontal axis. We're going to need to build a diagram that illustrates this. It's going to look something like this, where here's me sitting on the ground, or standing on the ground, and I'm going around the axis of the Earth. Let's try to illustrate here. That big fat arrow that you're going to see on these diagrams here, that's my motion as I go around the axis of the Earth once every 24 hours. And this arrow that's kind of pointing up towards the top of the screen is going to be a vector that illustrates the rotation of the Earth itself. Okay, that's kind of the axis of the Earth. Strictly speaking, it is a vector. There's a curl vector associated with the Earth. That's why I drew it as a vector. Anyway, that plane that you're going to be seeing there, drawn something like that, is going to be my horizontal. For wherever I'm standing at a given time, that's what I look like when I see off to the left and the right and forward and backward. That's my plane. Okay. And there's going to be a little vector that's perpendicular to the plane, like that. That's that red vector right there. So like if I were parked at the equator, I would be going around the axis of the Earth at a latitude of 0 degrees. But that rotation, that rotation is, that big fat gray vector right there, that's the normal vector, that's the axis around which I'm rotating. And that is at a 90-degree angle to what I would consider up. If I'm standing there at the equator, up is that way. It's perpendicular, it's normal, it's orthogonal to the direction of the axis of the Earth. My motion around the axis of the Earth is not horizontal at all. From my point of view, it's vertical. That's not vorticity. That's not that that's unimportant, but that's not relative vorticity, or planetary vorticity. On the other hand, if I were standing at the North Pole, as I rotated around my axis once every 24 hours, that is, just due to the rotation of the Earth, which is that big fat gray area up there, that is in the direction of the vertical axis at my location. I have a lot of planetary vorticity at that location because my rotation is in the horizontal direction, just as I go around, rotate the axis of the Earth. Of course, for most locations, I'm somewhere in between. For most locations, I'm somewhere in between having no planetary vorticity at the equator and having lots of planetary vorticity at the North Pole. If I'm sitting here at 39 degrees north, as I go around the axis every 24 hours, I am rotating so that my axis is just like the axis of the Earth. It's that big fat gray vector there, which is kind of, but not exactly, in the direction of my local vertical, which is that red arrow there. So part of my rotation is vorticity, the other part is helicity, but part of it, well, okay, so there is some idea here that as I go to different locations on the Earth, just sitting there at the surface of the Earth is a type of spinning with a horizontal rotation, but not all of it. And so, after a lot of math, you can show that this planetary vorticity turns out to be 2 omega sine phi. I didn't actually put on there, omega is the rotation rate of the Earth. 2 pi radians every 86,400 seconds. And phi is the latitude you're at. 2 omega sine phi. Survivors of classes like dynamic meteorology know that already. That's called the Coriolis parameter, which is F. F appears all over the place in fluid mechanics equations. If you're taking a class that involves any kind of fluid mechanics or any kind of atmospheric dynamics, F is all over the place. It turns out F is also the planetary vorticity. And notice how it depends on the, well, it depends on the rotation rate of the Earth, which doesn't change meaningfully from, over synoptic scales, and phi, the latitude. All it depends on is the latitude, which means a map of planetary vorticity would be about the boringest thing on Earth. Don't get me wrong, at every single location on the Earth, you could compute a value of planetary vorticity. It's just 2 omega sine phi. The only variable there is the phi. So you just plug in the latitude. But it would be a very boring map, because all it would be is a map that goes from 0 at the equator to a big number at the poles, and the contours would just be parallel to latitude lines. So you'd have high planetary vorticity at the poles and 0 planetary vorticity at the equator. But that does mean that you can advect planetary vorticity. I mean, anytime you have a wind from the north, you have positive planetary vorticity advection, because you are pulling air that has a lot of planetary vorticity towards a place that has less. And anytime you have a wind from the south, well, in the northern hemisphere anyway, you have winds that are giving a negative planetary vorticity advection, because they are taking air from a place that has low planetary vorticity, maybe even 0, toward a place that has more planetary vorticity. This is actually a thing. It's called the beta effect. Again, in some of your classes you either have had or will have. At some point you'll see that term, the beta effect, and it in fact affects how cyclones develop and so on. But that's not where we're going with this right now. What I want you to notice is, in practice, there's a reason why we lump these things together into absolute vorticity. Because it turns out advecting relative vorticity, the relatively easy, no pun intended, the relatively easy thing to think about where spin is just the spin, and advecting planetary vorticity, which is a somewhat more complicated idea about thinking about the roles of winds from the north and winds from the south, turns out it's totally unhelpful to separate those two effects. They both have exactly the same effect on the circulation. So we tend to just work with this idea of absolute vorticity instead, that combines our idea of planetary vorticity and relative vorticity. So these contours, the dashed contours on here, are contours of absolute vorticity. The software that made this plot already computed the relative vorticity at every location on this map based on the winds, and the planetary vorticity on this map just based on the latitude, and then added them together, called that absolute vorticity, and contoured it. Can WXP do that? Absolutely. No pun intended, absolutely. There's actually a variable in WXP called a vort that is absolute vorticity, and it will gladly compute that for you. And you can gladly then, just like on this canned map that came from the DIFAX service, you could make a map too where you would look for the solenoids that would have your absolute vorticity advection. In this case, I only highlighted areas that had positive absolute vorticity advection. But if you dig through some kind of archive of these plots, you're going to notice something important right away. They only ever show these maps at 500 millibars. As in, the isobaric level. How high above the ground 500 millibar level is, that's where they show absolute vorticity and the heights, and from which, with your eye, you can look for the solenoids and find absolute vorticity advection. You gotta wonder why. Why there? I mean, in fact, you can use WXP. You can make a map of absolute vorticity and heights at any pressure level. You want to do it at 1,000 millibars, knock yourself out. You want to do it at 200 millibars, knock yourself out. But we only ever really see it, or on a website or in a textbook at 500 millibars. And it turns out there's going to be a bunch of good reasons for that, but they all have to do with what positive vorticity advection actually does in the atmosphere. So what I'm going to do with the rest of this lecture is show you what positive vorticity advection does. Then, on the lecture that we're together online in Skype, I'm going to show you what we do with that in the context of like weather analysis and forecasting, and why 500 millibars, and how we can use it to talk about cyclogenesis, and how we can use it to talk about vertical motions in the atmosphere, and so on. But first we need to understand what the heck positive vorticity advection actually does. Okay. When you get these slides, they're not going to be animated the way they are on the screen, but you have access to this actual PowerPoint presentation, which you can load into some kind of PowerPoint viewer, and you'll actually see that there's animations on here. The animations are not a make or break kind of thing, but they might be helpful to you. Remember, troughs have positive vorticity. The wind, as it passes through a trough, is rotating. It is turning to the left as it goes through it. It is making a cyclonic turn. It's not going to even make one full rotation, but it's making part of a rotation over a course of a day or two as an individual air parcel scoots through this, trough in the jet stream or whatever, 500 millibar flow. In the same sort of way, over here in this ridge that's over here over the east coast of the United States, you can see this ridge in the flow here. Flow is rotating in a clockwise way, or an anticyclonic way. Again, it's not going to make even one full rotation as it goes through there, but it is rotating in a way that has negative vorticity, and that area between the trough and the ridge has no vorticity. The flow is no relative vorticity anyway. In fact, the flow is straight. It certainly still has planetary vorticity, and therefore still has absolute vorticity, but let's just focus on the relative vorticity for a minute. I want to indicate a little bit of a terminology here. This area that I have highlighted, like with those two orange arrows there, I would describe that as being ahead of the trough or behind the ridge. Now, because we have a trough across like Texas and New Mexico and Arizona. If you're not comfortable with those words, trough and ridge, let me know. Okay? Clearly we have this area over like Indiana and Illinois and so on where we are ahead of the trough. Why do we call that ahead of the trough? Because in Northern Hemisphere, mid-latitude meteorology, these features, we know that these troughs and these ridges are going to be moving off to the east with respect to time. So like that area over where the flow is kind of straight, which is currently over like Illinois and Indiana, that is ahead of the trough. The trough is still coming. It is behind the ridge because the ridge has already passed. Okay, we know that in mid-latitude Northern Hemisphere meteorology, all these weather features are going to be trying to move from the west to the east. Okay. That area ahead of the trough, behind the ridge, had no vorticity, no relative vorticity anyway, but it does have positive vorticity advection because the area to its upwind of it has more vorticity than it does. Remember, upwind of that area of positive vorticity advection, or PVA, there was a lot of positive vorticity. That area over like Iowa, Illinois, Indiana had no vorticity, so the wind is bringing air with more vorticity than the air there now has. That is positive vorticity advection. And for that matter, the area ahead of the next ridge or behind the next trough is an area of negative vorticity advection. It is bringing air that has less relative vorticity, in fact negative relative vorticity, toward an area that has no relative vorticity. So we have an area of negative vorticity advection, or NVA, and an area of positive vorticity advection, PVA. And they're not in the trough, and they're not in the ridge, they're between the trough and the ridge. Alright? So physically, what is positive vorticity advection? Well, what I like to tell students is to think about it this way. Is the process, positive vorticity advection is a process anyway, by which winds are bringing air that has more positive vorticity advection towards an area that has from an area that has more positive vorticity towards an area that has less positive vorticity, maybe even negative positive vorticity. So like for example on this map right here, A is in the trough. It has a lot of positive vorticity. The wind is rotating as it goes through there. At the location B, the wind is going in a straight line. There's no relative vorticity there. But location B does have positive vorticity advection. So at that location A, positive vorticity, a given air parcel has positive vorticity. It is spinning. Now, it's not twirling. It's just making that turn as it goes around the base of that trough. But it has to stop doing that by the time it gets to location B. It has to lose that spin. How do you lose spin? Well, let's think of this more generically. How does a figure skater lose spin? Again, if you bring this up actually in a PowerPoint viewer, you'll actually watch the animation. But basically, it's just a guy spinning here. Here's a figure skater. How does a figure skater lose his spin? Well, if you've ever watched the Winter Olympics, you know what they do. They put their arms out. Probably in a high school physics class or a college physics class, they even did that demo, maybe even using something as corny as a spinning chair, where they showed that if you spread your hands out, there's a conservation of angular momentum, if you remember that term from physics class, and your angular momentum is conserved, but your angular velocity decreases as you spread out. Spreading out the mass is a way of losing spin. Well, an area of positive vorticity advection is apparently a place where the air has to lose spin. The floor was turning as it went through the base of the trough over like New Mexico and Texas, and we have to lose that. That's strange. That isn't the way we tend to think of an advection, but in the case of positive vorticity advection, that's what you got to think about. You got to think about how this is an area where we will be spreading the air out. The air is going to have a way of spreading out. We don't use the word spreading out in meteorology. We call it divergence. Air will diverge. Okay? It'll spread out at this level as it has to experience that positive vorticity advection and lose some spin. So the air will come through the base of the trough, and then as it goes into that straightaway between the trough and the ridge, it'll have to spread out. Remember, air parcels are moving much faster through this jet stream than the troughs and the ridges themselves are moving. Think of the trough and the ridge right here as being like a hose. Okay, the water moves faster through the hose than like you moving the hoses around. Right? The trough and the ridge are going to move, but the air parcels are shooting through it. But between that trough and that ridge, where we had positive vorticity advection, the flow has to spread out. You can see the analogy of a hose doesn't really work anymore. I mean, hoses can't spread out. Divergence. Now, this is all happening at some kind of like jet stream level or 500 millibars or something like that. I didn't really think that all through as I was making these slides. But if you have this going on at 500 millibars, what's going on down at the surface below that? So if you have an area of divergence at upper levels, 500 millibars, upper troposphere, something like that, well, what is pressure at the surface of the Earth except the weight of the air above you? Well, I mean, that's one of the things you learn in ATS 113, right? Every intro student takes a test at some point that asks, what is pressure? It's pressure is the weight of the air above you. If we just took the mass that was above us and spread it out, there's now less air above us than there was before. That makes pressure at the surface fall. Positive vorticity advection aloft caused upper level divergence, which immediately meant pressure near the surface of the Earth, at the surface of the Earth, had to fall. Oh. And notice where that low is. I'm trying to illustrate it here in kind of a 3D perspective. That low at the surface is east of the ridge, east of the trough, and west of the ridge. It's under the area that was that positive vorticity advection aloft. The trough aloft is not directly above the cyclone at the surface. In fact, notice it tilts westward with respect to height. The surface low is at one location and the trough is west of it. We talked last time about the fact how these kind of weather systems tilt with respect to height. They have to, actually, in order for them to work. Again, if I made this map looking at it from above, this perspective might help you. So that L is the indication of the cyclone at the surface, and those kind of transparent purpley arrows there are showing us what the winds aloft would be doing. So we can see that the trough, which is over its axis is at like New Mexico and West Texas and so on, is well to the west of where the manifestation of the low pressure system is at the surface. The surface low is, right over basically Evansville, Indiana in this case. Oh. The cyclone is to the east of the trough, to the west of the ridge, and under the area of positive vorticity advection. Cool. And I beat this into the head of my ATS 113 students. I don't think any of you guys had 113 from me, but I'm guessing Mr. Ritz talked to you guys about that too. Even in those classes, students are told, well, I know what I tell my students in ATS 113. I say, even if you know nothing else about positive vorticity advection and vorticity and so on, know that PVA is associated with upper level divergence. At whatever level you're having the positive vorticity advection happening, that is a place where divergence is happening and the air is spreading out. Now, upper level divergence means things. Upper level divergence has all kinds of places that it keeps coming up in meteorology. For example, we just showed that upper level divergence means that the pressure is going to be low at the surface. Actually, just from what we've just seen, I'm not sure whether I would say the pressure is low or the pressure is falling at the surface. That's two very different things, right? The pressure being low versus the pressure is higher right now, but it's falling. That could be. I'll have to decide which one of those I think I mean. Or it could have to do with, like, upper level divergence can be part of the story of, like, rising motion and sinking motion for that matter too. Although upper level divergence will always turn out to be associated with uprising motion. Now you might think, oh, I get it. Air diverges aloft. We have upper levels, the air is spreading out in the upper troposphere, and air rises from the surface to take its place. It's not that simple. Although that's not a horrible way to think about it, but we'll talk about that in Tuesday's class. But this idea of this connection, if you only ever know that positive vorticity advection causes divergence at that same place, and then deal with what does the divergence mean, that would be okay. That would be a good place to start in understanding positive vorticity advection and what that means for weather. Because this is going to be part of the story about how cyclones change, how they go through their process of cyclogenesis, which is strengthening a cyclone by lowering its pressure, which is going to happen whenever there's a positive vorticity advection in the jet stream causing upper level divergence. Or the opposite pattern called cyclolysis. That's a hard word to say, cyclolysis. And cyclolysis is the process of the death of a cyclone. It's weakening a cyclone by increasing its central pressure. As the pressure gets closer and closer to normal in the middle of a cyclone, the winds are getting weaker, the rotation's getting weaker, the rising motions are getting weaker, etc. And that's going to be cyclolysis is going to be happening whenever the jet stream is not configured in such a way that you are getting positive vorticity advection. And we'll see plenty of examples of this in our Skype class. But this is why, as a dutiful young young atmospheric science student, I colored in my weather maps. I took my map that had dashed contours of absolute vorticity and solid contours of height, and I looked for my solenoids and I shaded in the areas with positive vorticity advection in red. Because I knew from my classes that stuff happens there. That was helping me identify areas where there was going to be storminess. But I didn't know why. I don't know if I just wasn't paying attention that a teacher taught it and maybe he was the best teacher in the world, or did he not tell us? I don't know. It took me years before I put this all together from other classes and so on, before I understood what was going on. That area, though, where that upper level positive vorticity advection is happening, particularly at 500 millibars, is going to be a big part of the story of cyclogenesis. It's going to be a big part of the story about rising motion in the atmosphere and so on. But exactly how and exactly why is a topic that I would rather talk to you guys more in person about. So now that we have kind of a basic understanding of relative vorticity, absolute vorticity, even planetary vorticity, and the basics that connect this idea of positive vorticity advection to whether stuff happens, like cyclogenesis and rising motions and so on, that's where I wanted to go with this online lecture. All right, let me know if you have questions about this, and I look forward to seeing you guys on Tuesday night.